Hello fellow viewers, welcome back to another video. So today we're going to be talking about diffusion. So what exactly is diffusion? Basically, diffusion is the random net movement of particles from a region of higher concentration to a region of lower concentration. Now diffusion can occur with or without a partially permeable membrane. So basically, a partially permeable membrane is a selective membrane which only allows certain molecules or particles to pass through. So let's say, for example, I have some big green molecules here, okay, but they're too big to pass through these holes over here, so they cannot pass through. Then let's just say I have these smaller pink molecules which are small enough to permeate through this membrane. So that's what a partially permeable membrane is. So diffusion can occur with or without a partially permeable membrane. So basically, it also goes down a concentration gradient. Now, what do I mean by down a concentration gradient? Alright, let me draw out something for you so that you can visualize this. Give me a moment. So that's the concentration on the y-axis, and over here we just have the regions. So this is... So for our region of higher concentration, I'm just going to call it A. So this is A. It's just a rough sketch, yeah? Don't mind me. And for our region of lower concentration, we're going to call it B. So this is B. Okay? So A has obviously a higher concentration compared to B. So now we know that diffusion is a random net movement of particles from a region of higher concentration to a region of lower concentration. That means that particles from this higher concentration will be moving to the region of lower concentration. So that's what we mean by down a concentration gradient. We remember that a gradient is basically just a rise over run, right? Yeah, so this is down, going down. The particles are moving downwards this way. They're going to the lower concentration region. That's what diffusion is. So this is the particles are moving. That's basically diffusion for you. Alright, so we've done that. We also have to know that diffusion only occurs in fluids. Now, what are fluids? Fluids are basically anything that is a liquid or gas. So for example, a liquid would be like water and a gas would be like oxygen. So basically a wooden table, that is a solid, that is not a fluid. Yeah? So let's move on. Basically, diffusion only occurs until diffusion just stops when both sides, both regions are of same concentration. So basically, let me draw another graph for you. So basically, this is my region A again. This is my region B. So basically, when both sides are of equal concentration, the net movement will be zero because the gradient is zero. Yeah? So the net movement is zero. So when the net movement is zero, diffusion technically stops there. But that does not mean that the particles stop moving. The particles will continue to move. Now, what do I mean by that? Okay, so let's take a look at this example. From region A, I have a ungodly amount, a lot of green particles. And in region B, I have a few pink particles. Yeah. So basically what diffusion is that these green particles are diffusing into the spaces between these pink particles. Then these pink particles are technically also diffusing into spaces between those green particles. Because from their viewpoint, from the green side's viewpoint, the pink region does not have any green molecules, so they want to even it out. They're just moving into the pink places. But from the pink's point of view, the green region does not have any pink particles, so they're just moving in there to even the concentration out. So basically that's what it is. So when we say that the net movement is 0, since it's just for example, we're saying that concentrations in both regions are equal. So as you can see, I can just take out a chunk here. This is region A, this is region B, and you can kind of say that they're kind of equal in terms of concentration of pink and green particles. But when I say that the net movement is 0, that does not mean that they stop like moving. They will still move. It's just that they're in a state of equilibrium. That means equilibrium basically just means a state of balance. So basically when they're in a state of equilibrium, the molecules are actually moving equally in both directions in each region. So let's say if I have a pink molecule move to region B, then I'll have another pink molecule from region B move to region A. So basically that's what happens at equilibrium. Okay, the particles will still move, it's just that there's no like singular direction moving to one region only. Yeah, so that is equilibrium. So there are technically two factors that I'm going to teach you today that affect rate of diffusion, and that is relative molecular mass and temperature. So yeah, let's start with relative molecular mass, or as I like to call it, your MR. So basically every single molecule, right, they have their own like sort of mass. Okay, so let's just I'm gonna think of two random. Let's do ammonia gas and oxygen gas. So let's compare these two. These two have different relative molecular masses. For ammonia, its relative molecular mass is 17. For oxygen, its relative molecular mass is 32. Now, if you don't understand what relative molecular mass is, it's okay. I'll cover it in another video. But for now, you just need to understand that. For example, let's just pretend that the ammonia is a smaller ping pong ball. Let's just pretend this is a ping pong ball. Yeah. And let's just pretend that the oxygen molecule is a. Let's just pretend it's a bowling ball. Yeah. Just wrong color. Pretend it's a bowling ball. So basically, comparing these two, the bowling ball is definitely way heavier than a ping pong ball. So therefore, if I were to push it in one direction, the ping pong ball would technically move faster than the bowling ball. Yeah? So same thing with this one. The lower your relative molecular mass is, the quicker your rate of diffusion. So basically, if we compare ammonia gas with oxygen gas, ammonia will have a quicker diffusion rate. So let's just say I have two tubes here. And wait, no, hold on. Let me do it horizontally. Okay, this is from a eye level view. They're resting on the ground. I have some oxygen gas here and some ammonia gas here. So obviously, since the MR of ammonia is lighter, it will obviously move, it will diffuse faster to the end, because this region has a lack of ammonia. There's a higher concentration of ammonia here than compared to here. As for the oxygen, it will also diffuse all the way to the end because there is a higher concentration of oxygen here. But because the relative molecular mass of oxygen is higher than the relative molecular mass of ammonia gas, this means that oxygen would diffuse relatively slower compared to ammonia gas. So that means that ammonia gas will reach the end way quicker than the oxygen will. Alright, understood? Okay, so we move on to our second factor, which is temperature, which also affects diffusion rates. Now, why does temperature affect diffusion rates? Now, we know that high temperatures would mean that there is a increase in energy. And that increase in energy would indicate that there is an increased kinetic energy. And if there is an increase in kinetic energy, that means that something will be moving faster. So if we just apply that logic into the molecules right now, I'm just going to pretend, okay, just draw two beakers, one cold and one hot. So this is your cold bath, this is your hot bath. Let's just say I throw in a test tube of gas. Let's do, let's just, hold on. Alright, let's just do ammonia gas. So let's just pretend we throw in some ammonia here. Okay. So basically, if I put it in the hot bath, that means that this ammonia gas in here is going to gain heat. And since it gains heat, right, that means that kinetic energy also increases, and thus it will start to move around faster. And if it starts to move around, moving around faster, that means it will diffuse quicker too, because it will get around places quicker. So you'll diffuse out of this test tube into the area where there is a lower concentration of ammonia gas. Well, as if I put it in a cold water bath, that would mean that there's lesser energy in this, and thus kinetic energy would just decrease. Thus it would diffuse around slower. Thus it will take a longer time for this ammonia in the cold bath to diffuse out into the regions with lower ammonia gas. So that does it for today. I hope you do understand what diffusion is now, or at least get a simple idea of what it is. So thanks, bye.